Okay, so sorry for that. Let me start again. So, hello everyone. This is the start of a seminar series. It's titled Stringy Seminars. And the first talk of this series will be given by Hassaan Saleem. And Hassaan is from University at a PhD student at University at Albany. And today he is going to give a talk on topic non-supersymmetric strings on ADS3. So, welcome Hassaan to this seminar series. And yeah, you can start your topic.
Okay,
Thank you.
thank you for the invitation. Thank you for the introduction, and thanks for the invitation to give this talk. So I'm going to talk about non-supersymmetric strings on ADS3. So let's start from the common lore about superstring theories. So from popular science, most people know that there are 5 superstring theories without tachyons, and they are called type 1, type 2a, and type 2b, and there are 2 heterotic theories. All of these theories are supersymmetric. They're called superstring theories, and they don't have tachyons. So what are tachyons, first of all? So tachyons are particles with negative mass squared, right? And it's a very unphysical property to have, because if you have negative mass square, it also implies that you will always travel faster than the speed of light. And if you have tachyons in your theory, it signals instabilities of the vacuum. So the vacuum is not stable anymore. It will decay into something else. So therefore, you don't want tachyons in your theory. Most non-supersymmetric string theories do have tachyons. For example, if you have gone through any course on string theory, you would have certainly come across bosonic string theory. Bosonic string theory doesn't have supersymmetry, and it has tachyons. Famously has tachyons. So therefore, non-supersymmetric string theories don't direct a lot of attention. And one of the reasons why that's the case is the presence of tachyons. Now, there are 10 known non-supersymmetric theories that don't have tachyons. So one of them is called the heterotic O16 cross O16 theory. This came out in the late 80s. And then there are 2 or more theories, which are, which are called open or orientifold theories. They're called Sugimura model and Segnori model. So in this talk, I'm going to talk about this first theory, heterotic O16 cross O16 theory. It doesn't have any open strings. It only has closed strings. Okay, so one thing that we know about supersymmetric theories or string theories is that loop corrections vanish in superstring theories. That's a very lucrative or a very attractive feature of these kind of theories. So we can have loop corrections to string theory action that can give rise to a cosmological constant. But these, as I said before, that these loop corrections do vanish in superstring theories. But in non-supersymmetric strings, there is no guarantee that these loop corrections will vanish. So that's one thing that we have to keep in account, take into account when we are studying non-supersymmetric strings. Now, one question that you can ask now is that, so since loop corrections are present in non-supersymmetric strings, then the question that you can ask is that, can you uplift an ADS spacetime to deSitter spacetime by these loop corrections? So if you start from an ADS spacetime, suppose that you have a tree-level solution of ADS spacetime. If you include this one loop correction, is it big enough that your ADS spacetime will uplift to deSitter spacetime? That's a question that you can ask, for these non-supersymmetric strings. Another question that you can ask is that, so if I construct some non-supersymmetric, backgrounds, are they stable? Now, what do I mean by stable? There are 2 kinds of stability that you have to talk about. One of them is called perturbative stability. How do you know if a particular vacuum is perturbatively stable? So it depends on what kind of vacuum you have. If you have a Minkowski vacuum, it just means that all the perturbations that you have, scalar perturbations, they are, either massless or massive. By that I mean their mass squared is either 0 or positive. But if you have ADS spacetime, then the picture is a bit more tricky. If you have ADS spacetime, then it turns out that your mass square can be slightly negative, but not very negative. There is a bound, a lower bound, and you cannot go below this bound. And this bound is called BF bound. So if your fluctuation is a scalar fluctuation, then your mass square should not go below this bound. Now, this L is ADS radius, and this D is the space dimension. So I'm talking about ADS D plus 1 space-time, which means that D is the space dimension. So, for example, if you are in 4-dimensional ADS, 5-dimensional, sorry, then your D is 4, and D squared over 4 is 4. So the bound becomes the -4, divided by L squared. But if your fluctuation is not a scalar, if it's a P form, right, then you have to include this P here as well. So both of these are called BF bounds. So stability for an ADS background means that all the fluctuations are above or at these bounds. But there's another kind of stability called the non-perturbative stability. What does that mean? It means that you cannot have you cannot have bubbles of true vacuum popping out and expanding at a very fast rate. So suppose that you start with some background, and that background is a false vacuum. It's not a true vacuum. So the story here is a Coleman-DeLucia-like story. And if you find out that the bubbles of true vacuum will pop into existence at a very rapid rate, then you don't have stability under non-perturbative processes. So you have to ensure that these bubbles are not forming at a very rapid rate, right? Okay, so therefore you have two different kinds of stabilities here. Now there is one no-go theorem that I would like to mention here. So there is a very famous no-go theorem when it comes to getting deSitter from some compactifications. That no-go theorem is called Maldacen and Nunes theorem. It came in 2001. And the argument is pretty simple, actually. It doesn't even assume supersymmetry. So there is a very similar kind of theorem that was proven by Bazil and Nanza in 2020. And they proved it for this following action. Now, you can see that some terms in this action are very familiar. For example, this R term is just a Ricci scalar term. This term is the usual term that you see in string theory actions in the Einstein frame. And this term is the usual, H, NSNS flux term. But what is this term? This term is something that you see that come from one loop corrections. In superstring theory, you will not see this term, this kind of term. But in non-supersymmetric string theories, where you do have one loop corrections, they usually take this form for some T and for some gamma. So therefore, they took this action and they showed that if you compactify this action on some space Y, where the dimension of Y is Q, and Q has to be bigger than P plus Q because we want to, have an H flux over Y, and that can't happen if the dimension of Y is not bigger than P plus bigger than or equal to P plus 2. So if you compactify this action on this particular space Y, then you can never have deSitter on Minkowski vacuua if this condition is satisfied. Now, this alpha comes from this term, this gamma comes from this term, and P comes from here. So you just need to see if this particular thing is satisfied. If it is satisfied, then you can't have deSitter or Minkowski vacuua. But you can see that there is a problem here. The problem is that you are assuming the existence of magnetic fluxes only. You're only wrapping the internal space with H flux, not the Lorentz part. So if you have fluxes on the Lorentz part as well, which means that you have electrical fluxes as well, then this theorem doesn't directly apply. Okay. Now there have been some backgrounds that are studied for O16 cross O16 theory. For example, in 2022, this study was performed over for ADS3 cross S3 cross S3 backgrounds over S1, right? By over S1 I mean that you start with O16 theory on a string scale S1, and you compare, the rest of the 9 dimensions make this background. And this background was also studied in this paper in more detail. Now, in this background, they had, an H1 flux on ADS3, which is called N1, and an H1 flux on S3, which is called N5, and another H1 flux on H3 flux on the other S3, which is called N5 hat. Now, in that paper, they saw if deSitter uplift happens, and it turns out that it doesn't happen, right? Secondly, they also checked the perturbative stability of scalars in ADS3, and it turns out that all scalars are above or at the BF bound, but they didn't check stability of other kind of fields, for example, vectors. They didn't check, quantum, I should say non-perturbative actually. They didn't check non-perturbative stability. So we don't know if this background is, stable under non-perturbative processes like Coleman-DeLucia bubbles. Now, we will try to answer the same question for ADS3 cross S3 vacuua for O16 cross O16, theory on a string scale T4. So you can think of it as ADS3 cross S3 cross T4, but T4 is frozen at the string scale. It's not dynamical. So we'll ask the question that can you get an uplift to deSitter in this particular background, and can you also see if there is perturbative stability for this background? So why are we studying this background? First of all, we are studying this background because of many reasons. One reason is that there's a very rich T4 moduli space, right? So you can look at different extrema in the T4 moduli space and study the theory around those points. There are some results that can be calculated analytically for this particular background. For example, if you look at the previous background that I mentioned, for that particular background, there are some results that can't be calculated analytically, but they can be calculated analytically for this particular background. And this background is very similar to ADS3 cross S3 cross K3. So this is one background that we want to study in the future. So if you just replace this T4 by K3, you get this background. So it's a bit like that. And we'd also know that some points in the K3 moduli space, they are just orbifolds of T4. So if you start with this background and do an orbifold on T4, then you can get, a point in this particular moduli space. So that's another motivation to study this particular background. So let's start the first part of the talk, or let's try to answer the first question: that can you get uplift to deSitter? So the O16 cross O16 heterotic theory has this action in the string frame, where you have the usual suspects. So AH3 is just the NS3 form, and you know that in heterotic theory we have a gauge field. So F2 is just the heterotic gauge field string. Now, the metric on the background that we are studying will be taken in this form, where you can see that you have a volume modulus for the S3 part, but for T4 you don't have a volume modulus, because I said earlier that we are not considering the fluctuations of the T4. Now, chi is the volume modulus of the sphere, and this d omega 3 cube square is the metric on a sphere with radius L. Sometimes people take L square out of this metric, but I'm just taking this to be the metric on the sphere, on a sphere with radius L. Okay. Now let's write down the potential that you get that you get in 3 dimensions. So by 3 dimensions, I mean ADS3. So there are various places from where you will get this potential. I'm not giving you all the details here, but this term comes from the curvature of the sphere. This term comes from the H3 flux on the sphere. And this term comes from the electric flux on ADS3. So you have ADS3 cross S3. There is an electric flux on ADS3, electric H3 flux, and you have an H flux on S3. So this term comes from the flux on S3. This term comes from the flux on ADS3, and this term comes from the flux, the metric, sorry, the curvature of S3. Now, if you have this, potential, you have to take its derivatives with respect to phi and chi and set them to 0 and see what solution you get. I have explained some of the notation that I'm using here. Some appearances, this V is just a number to parameterize the volume of the torus. So since we have T4, the volume of torus should be something like length to the power 4. And we do know that alpha prime has units of length square. So if you put the volume equal to some dimensionless number times alpha prime squared, then V has to be dimensionless. That's why I'm introducing V. And you can see that V makes an appearance here, for example. Now, let's take this potential and take its derivatives with respect to phi and chi and put them equal to 0, and let's see what we get. So if you take the derivatives, you get these 2 equations. And if you solve these equations for phi and chi equal to 0, then you get these solutions for L, where just to remind you that L is the radius of S3 and GS is just the G string. So you get these solutions, and if you put these solutions in the potential, the minimum of the potential is something like this, and you can see that it's negative. So since the minimum of the potential is negative, it means that you have an area spacetime, and the cosmological constant in 3 dimensions is just V minimum divided by 2. So you can see that the cosmological constant is negative, which means that you have an area spacetime at the tree level, which was expected. Okay. Now let's add the one loop correction. So I can, if you ask me, then I can tell you how one loop correction is derived. But I can just tell you that it comes from integral of the partition function over the fundamental domain. So if you take the integral of the torus partition function over the fundamental domain, then you get the one loop correction. The details are given in the paper, but I can answer if you ask me that how is this derived. So you add this term to the potential that I showed you earlier, and you get the one loop corrected potential. So if you add this term and then take the derivatives again, with respect to phi and chi, and see what the equations you get, then you get these 2 equations. Now, the thing is that you can have these 2 equations, but these 2 equations need to be solved for L and G. Now, you can see that there is the subscript O here, LO and GO. What does that mean? It means that now these quantities are one loop corrected quantities. So they are still the radius of the sphere and G string, but they are one loop corrected quantities. So one good thing about this background is that you can solve these equations analytically. If you look at these analog of these equations for ADS 3 cross S3 cross S3 that I mentioned earlier, there you can't solve these equations analytically, but here you can. So one equation that you can deduce from these two equations is the relationship between GO and LO, but you still need to solve for LO, right? And you can solve for LO. The solution is not very pretty, but it can be written down. And this is the solution. It's not very pretty, but you can write it down in terms of defining other things, for example. But the solution for LO is known as an analytic function. Now, one thing that needs to be checked is the following. If you go back and look at the solution for G, well, not the solution, but the relation between GO and LO, you see that there is an N1 in the denominator. So you may think that, well, is there a divergence in GO? Because when N1 goes to 0, GO seems to be diverging. So, but that's bad. I'll tell you why that's bad, but we need to ensure that GO doesn't diverge. So what can we do to ensure that? We can study the small N1 behavior of GO and LO. And when we do that, we get these two series as a series in N1 squared, right? And you can see that when N1 goes to 0, the limits are perfectly fine. Neither GO diverges nor LO diverges, right? So small N1 behavior is fine. Now, if you take those solutions that I showed you earlier and put them back in the potential, you get the minimum of the potential as a function of LO and GO. Now you can see that the minimum of the potential now has a negative part, but it also has a positive part, and this positive part came from one loop correction. So there is hope that you can get deSitter uplift. Now I'm going to give you a spoiler: deSitter uplift still doesn't happen, because although you do have a positive part, this positive part is never positive enough to give you a deSitter uplift. So it means that you still have an area space-time. So if you have an area space-time, then you can write down the expression for the ADS ADS radius, and you can write it down in terms of LO and GO, and this is the expression. Now we're going to plot some things. So you can plot LO as a function of N1 flux, and there is dependence of LO and other quantities that I will plot on two kind of fluxes, N1 and N5. So if I have to accommodate both of those dependencies, then what I can do is that I can plot these quantities as a function of N1, but I do that for different values of N5. So for example, this blue graph is plotted when N5 is 1000. This graph is plotted when N5 is 2000, and so on. Right, and you can see that as N5 becomes bigger, LO becomes bigger as well. But when N1 goes to bigger values, the change is not that much actually. So there is much stronger dependence on N5 as compared to N1. Same is the case with GO. Now you can see that GO never diverges. Even when N1 goes to very small values, it goes to a steady value. It plateaus, it saturates. It never goes to a very big value. I don't want to scroll all the way to very old slides, but if you remember the tree level solution for G, it was proportional to 1 over N1, which means that when N1 goes to 0, G diverged, but that's not the case if you include the one loop correction. So therefore, it's sometimes said that one loop corrected non-supersymmetric strings, they don't like strong coupling, because you can see that G never goes to big values here. So there is no strong coupling here. Okay. Now this is one of the most important graphs. If you plot V minimum, you can see that as N5 goes to big values. For example, purple graph is for N5 equal to 1000. And when N1 goes to small values, this V minimum tries to be as positive as it can, but it can never become positive. It still stays negative, which means that the uplift never actually happens. It's always an area space-time, probably with a small cosmological constant, but a small negative cosmological constant. It never becomes a positive cosmological constant. Okay, so the first question has been answered, that the deSitter uplift is still not happening. What about stability? So for stability, let's start with a 6-dimensional effective action. So start with a 10-dimensional action, then compactify it on a torus, and write down the 6-dimensional effective action. Now you will get some extra terms. So you get these extra terms, these two terms. Now, what are these terms? These terms come from torus moduli. So these sigmas are 80 scalars coming from T4 compactification. So T4 moduli space is 80-dimensional. Why is it 80-dimensional? Because you have 64 moduli coming from Wilson lines, 16 moduli coming from the metric tensor, and 6 moduli coming from the B field. So you have 80 scalars. So therefore, you will get kinetic terms and potential terms for these 80 moduli. Okay, now there's one unconventional piece of notation here that I'm using. This lambda is the one loop correction to the potential. This lambda is not a cosmological constant. I know that it's a very unconventional way to write it, but this is what we have used, so that's why I'm using it here. Now, before I talk about stability, let me go back and go back to a no-go theorem that I mentioned earlier and put it in the context of our work. So the no-go theorem that I mentioned earlier said that if you have magnetic flux, then you can't have deSitter or Minkowski. So how did they prove that? I mean, I'm not going to give you all the details, but what they showed is that if you start from, so in our context, if you start from a 3-dimensional maximally symmetric space. So for example, you know that ADS spacetime and deSitter spacetime, Minkowski spacetime, all of these are maximally symmetric spaces. So suppose that you have a background which is M3 cross S3, where M3 is a 3-dimensional maximally symmetric space. And we do know that for 3-dimensional maximally symmetric space, R mu nu is some cosmological constant times G mu nu. Right now, this I'm using omega for cosmological constant because I have used lambda for something else. So that's why. So in the theorem, what they show, how did they prove this theorem? They showed that the integral of the cosmological constant over the internal space, which is S3 in our case, is equal to this term. Now forget about this term right now, but they showed it that it's equal to this term, and this term is negative. And this term came from the magnetic flux, the flux over S3. And since this term is negative, it means that the cosmological constant has to be negative, which means that deSitter and Minkowski are ruled out. But when you have an electric flux as well, then you get this term as well. And now you can't say that this whole term, that this whole thing is zero. You can't say that, right? So therefore, the theorem has to be modified. Now, what do I mean by that? I don't mean that the conclusion has to be modified. The proof has to be modified. So the thing that has to be modified is that you have this term, but if you have a maximally symmetric space, then the H field on the M3 part can only be proportional to the totally antisymmetric tensor. And if you use this expression here, you can show that this whole right-hand side becomes this. And now you can see that it's negative. And since it's negative, it means that the deSitter vacuua are ruled out. So it's not surprising that we didn't get the deSitter uplift. We should have expected it anyway. Okay, so let's go back to the question of stability. So, the action that I showed you earlier, this action, you can start with this action and write down the equations of motion for, the metric tensor for the B fields and the dilaton phi for some particular background. And the background is that the dilaton is 0 for the background, and there are no Wilson lines, and there are no torus moduli at the back for the background. Well, not that we don't have any torus moduli. There are no fluctuations for the torus moduli. That's what I mean. So if we are studying ADS 3 cross S3, then the Ricci tensor for the ADS 3 part takes this form. The Ricci tensor for the square part takes this form, and the cross terms are just 0. So this mu, these mu and nu indices, they live on ADS 3. These A, B indices, the Latin indices, they live on S3. Okay. So if you add up these two, add up the contributions to Ricci scalar coming from these two contributions, you get this. Now, the background H field is defined like this. This part lives on the ADS3 or ADS3 component, and this part lives on the S3 component. Now, what are these curly L's? Well, these curly L's are not arbitrary. You can use equations of motion to write these down in terms of, the one loop corrected sphere radius and the one loop, correction to the potential. So, and you can get this expression for curly LO and this expression for curly ADSO. So these curly L's are not arbitrary. They are written in terms of L and lambda. Okay. Now let's introduce perturbation. So the previous slide was about the background solution. Now what we're going to do is that we're going to perturb around this background solution and see that see if all the mass squares of the perturbations are above the BF bound, as I said earlier. So let's introduce perturbations in the metric and the B field. So for example, if you look at this part, the perturbation in the G mu nu part is split up into two different contributions. So this contribution is the traceless part, and this contribution is the trace part. Similar is the case here. This is the traceless part, this is the trace part. So therefore it says H and K are traceless. And for B field, you can write down your perturbations in terms of vectors because of 3 dimensions. Well, yeah, okay. And same is the case here. So if you introduce perturbations like this, what you can do is that you can take these perturbations, put them into equations of motion, and write down the equations of motion for the perturbations to the linear order only. Okay. But before you do that, you have to talk about gauge fixing. So when we study the equations of motion for metric or for B field, there is always some gauge freedom. So we have to fix that gauge freedom first. So we take Lorentz-like conditions. What we do is that any field that has an index over S3, which means it has either A or B, for example, if you contract that with the covariant derivative, then that covariant derivative has to be 0. So it's a bit like Lorentz, Lorentz gauge. So for example, metric, so G mu A has this A index. If you contract it with the covariant derivative, then it has to be 0, and similar is the case here. But since we split up these perturbations like this, right? So you can write down these Lorentz conditions in terms of the perturbations, and you get this. Same is the case with B field. So for example, if you go back and see, this B mu A has, this A index, which means that C has to satisfy a particular gauge condition. There is no A index here, but there are 2 indices here. So it means that V will have to satisfy a condition. And you can see that, yeah, these are the 2 conditions that you get, from Lorentz gauge condition. Okay, now you have fixed the gauge as well. Now what you have to do is, so before I talk about this slide, so until now you have introduced perturbations and you have fixed the gauge, right? Now what to do? You can write down equations of motion now, right? But those equations of motion need to be, broken down into different components. So for example, in quantum field theory, we, do it very, very frequently that we write down equations of motion and then we break them into Fourier parts, right? We do a Fourier analysis. What you can do here is that you can write down, your equations in terms of something called spherical harmonics over S3, right? And analyze different components separately. So for that, you need to break down every field in terms of spherical harmonics over S3. So there is an S3 in our background, that S3 that I'm mentioning. Okay. So how do you decompose different kinds of fields over spherical harmonics over S3? So if you have a scalar field like this, you only get these kind of terms. But if you have a field that has an index over S3, which is, for example, S mu A, it has an index A, which lives on S3, then you have to introduce some other kinds of spherical harmonics, which are called YA, and these are called vector spherical harmonics. So there are 3 kinds of terms that come here. One of them is called YAL1, YAL-1, and there's a third kind of term, which is the derivative of this previous spherical harmonic, because it also carries an index. If you have a field that has 2 indices over S3, then you can have tensor spherical harmonics, 2 kinds of them. Then you can take the derivative of the vector spherical harmonics, and then you can take double derivative of this spherical harmonic. All of these carry 2 indices, right? We don't have any field that has more than 2 indices, so we don't need to worry about any field that has 3 indices, because that's not in our case. That's not true in our case. Now, what if we break fields down like this and then impose these gauge conditions that I mentioned earlier? Well, if you do that, then you get equations like this, that, for example, it tells you that these terms should vanish, for example. And this one says that KL plus minus 1 should vanish. It means that this term should not appear and this term should not appear, and so on. So gauge fixing actually renders some of these terms 0. Okay, So if you break down, your fields in terms of spherical harmonics, the fields that have, a zero in the second argument here are called scalar fields. If you have fields that come with 1 here or -1 here, they are called vector fields. And you can already see that, for example, here, S is a vector. It's S mu. If you have any fields that have 2 here, they are tensor fields, but I'm not writing it down here. Okay. Now, you can write down all the scalar equations. I'm not going to show you the equations, but I can show you the equations if you want. I have some extra slides at the end, but they're very messy. Now, one equation is very important here, and I will mention that equation. One equation that you get is this, right? Now, this curly M is just the modes of M. And what is M? If I remind you, M is just what appeared here in the trace part of the metric tensor. N is what appeared here in this trace part of the internal metric tensor, right? And phi is just a dilaton. So you get this equation where curly M is just the modes of M, curly N is just the modes of N, and this capital phi is just the modes of dilaton. Now you get this equation, and you can see that this equation is non-trivial if L is not equal to 1 and L is not equal to 0. If L equals 0, for example, then the left-hand side is just 0, and the equation is trivial. If L equals 1, then again, the left-hand side is trivial, and you have no equation. So only for L greater than or equal to 2, you have a non-trivial equation, which means that you can use this as a condition, so this thing equal to 0 as a condition only for L greater than or equal to 2. Okay, but for L equal to 0 and L equal to 1, you can't impose this condition because the equation is just trivial, which means that our analysis has to break down in 3 parts. One part is where L is greater than or equal to 2, and the other 2 parts include L equals 0 and L equals 1. So we have to do these 3 different kinds of, we have to treat these three different kinds of sectors, separately. Okay. Now, what I'm going to show you now are called mass matrices, and I'll explain what mass matrices mean. So they will come in form of equations, but you can also write them in forms of matrices. So let's talk about the sectors L greater than or equal to 2. So for L greater than or equal to 2, you get this mass matrix. So what is a mass matrix, first of all? You can see that if you look at the left-hand sides of these equations, you can see that it's just Laplacian of something. Laplacian of M, Laplacian of N, U, and V. So you can write down this whole equation as Laplacian of a vector that has M, N, U, and V, right? And you can see that on the right-hand side, you have some numbers multiplying by the very same field. So M, N, U, and V. There is no, U here. So the term just has 0. There is no, they're all, there's no V here. So the term multiplying 0, V is just 0. And there is no M or U here. So the terms multiplying, so the coefficients of those two, fields are 0. So you can see that this whole equation is just Laplacian of a vector, and the vector is M and U and V, equals a matrix multiplied by that same vector, right? And the matrix entries are given in these equations, right? So this matrix that I'm referring to is the mass matrix, right? Now, if you have to find out, the eigenvalues, if you have to find out the mass squared of these, fields, what you do is that you find the eigenvalues of the mass matrix. That's how you find out the mass square of these fluctuations. So what we're going to do is that we're going to find out the eigenvalues of this mass matrix and plot them as functions of fluxes and see if they ever violate the BF bound. So that's the plan. Okay. Now let's do it for this particular mass matrix. So you can see that this is a 4x4 mass matrix, which means that they will have 4 eigenvalues. That there will be 4 eigenvalues, right? So if we plot these eigenvalues, against n1, for example, you get this. Now you can see that this red eigenvalue is never negative, so it's never going to violate the BF bound. The green eigenvalue is never negative. The orange eigenvalue is never negative. It does go to 0, but it never becomes negative. But this blue eigenvalue, although it's hard to see, but it is a bit negative, right? Now, if I remind you, I told you that the BF bound for scalars in ADS-D plus 1 is minus D square over 4. Now, if you have ADS 3, then D is just 2, right? which means that d squared over 4 is 1, which means that the BF bound is -1, right? It means that if we ever get an eigenvalue that goes below -1, then the BF bound is violated. Now, it's hard to see in this graph, but this blue eigenvalue, although it's a bit negative, it never goes below -1. The value that it saturates at is like -0.67. Okay, so this was for L greater than or equal to 2. Well, I'm doing it for L equals to 2, but you can do it for L equals 3 or 4, and those eigenvalues are even better. They never even become negative, right? So there is no BF bound violation here. Now let's consider L equals 1. Now for L equals 1, it turns out that one of the equations that I showed you earlier, it becomes trivial. Why does it become trivial? Because there are some residual gauge transformations that you can use to render some of the fields 0, right? So for example, you can see that here you have phi. Phi didn't appear before. So here phi was not a thing, right? Why was phi not a thing here? Well, because we could use this condition here and I could eliminate phi in terms of M and N. But I can't use this condition for L equals 1. So phi can appear. So therefore phi is here. So you see that therefore you have to do this analysis differently for L equals 1 and L equals 2 or L equals 0, for example. So you have 3 equations now. One equation just becomes trivial, the equation that I showed you earlier. Therefore, the 4th eigenvalue is unphysical because it can be removed by gauge transformations. So now you have a 3 by 3 mass matrix. Therefore, you will have 3 eigenvalues, and we can plot them against fluxes, and you get this. Now, this green and orange, well, they're always positive, no problem there. But this blue eigenvalue, now you can easily see that it's negative. And it's not easy to see, but this blue eigenvalue is exactly at -1. So here it's exactly at -1, which means that it saturates the BF bound, but it doesn't violate it because it never goes below -1. Okay. Lastly, let's talk about L equals 0. Now for L equals 0, you get another equation which is like it's unphysical, which means that you can remove it by gauge transformations, and now you get just 2 equations. And this time you don't even need to plot the eigenvalues. Why? Because you can just calculate the eigenvalue for this mass matrix, and it turns out to be this, and you can show that both of these are positive because you can use this inequality to show that this whole thing is positive. But we can still plot them, and if we plot them, sure enough, they are positive. So it's not a surprise that they are positive. Now, these eigenvalues, apart from this L equals 0 case, you see that I never wrote down the analytic expressions for these eigenvalues because it's very hard to calculate. Actually, we think that the analytic expressions are not even possible. For example, if I go to this mass matrix, analytic expressions for eigenvalues of this mass matrix are not available, right? So can you write down anything that is analytic for these eigenvalues? Well, there are some things that we can write down. One thing is that you see that these eigenvalues saturate at a particular value for large N5 and a particular value for small N5. So can we predict these saturation values analytically? Well, the answer is yes, we can do that. So let me come here. So one thing that I need to mention here is that you can see from the equations of motion that I mentioned in the very start of the talk that there is only one thing on which the eigenvalues depend on. So the dependence on the fluxes comes from this dimensionless parameter, which is S, right? So large N5 behavior just means large S behavior, but you can see that large N5 behavior also means large lambda behavior or small N1 behavior. So they are the same thing. So if I want to know what value eigenvalue saturates at for small N5, you can see that small N5 behavior is the same as small lambda behavior because you just need to make S small, right? But lambda comes from one loop corrections. And if lambda is 0, it means that there is no one loop correction, which means that you again have the tree level solutions. So small N5 behavior is the same as small lambda behavior, which means that you have the tree level behavior. So small N5 eigenvalues are the same as lambda going to 0 limit. And you can easily write down what the eigenvalues are for the tree level solutions. The complication comes from the one loop correction. So if you compare these values with the values that you're getting numerically here, here, and here, you get a perfect agreement. What about these, saturation values? Can you predict these ones? Well, here you have to see that you have to talk about the large N5 behavior. But again, since the dependence is only on this particular parameter, large N5 makes S big, but you can see that small N1 also makes S big. So it means that large N5 behavior should be the same as small N1 behavior. And I'm not going to scroll to that slide, but some slides ago, I showed you the expressions for small n1 when I said that, oh, there was a problem at small n1, so we need to check the behavior at small n1. So we can use those expressions to write down the small n1 behavior of these eigenvalues. And it's not very beautiful. It's messy, but you can write it down. No, it's not very beautiful, but you can write down what these four eigenvalues will go to when n1 is small or n5 is big, same thing. And these four expressions come out. And these expressions are given in terms of some other parameters called xi, a, and b, and they are given in terms of L. So they are not very beautiful. They're just messy, but you can calculate them. So let's see if we have an agreement with the numerical results. So for L equals 2, you can write down the four eigenvalues, and they turn out to be 16 and 65 and 23. So if we go back to L equals 2, you can see that, yeah, 64, 16 here and 35. So you get, an agreement. And the fourth eigenvalue, as I told you earlier, it was not at -1, but it was above -1. It was something like negative 0.67. So if you look at the numerical result that we get here, yes, it matches as well. And you can see the same thing for L equals 1 and L equals 0, the numerical matches there. So at least you can predict these saturation values in analytic form. Okay. Another thing that we can do is that we can write down the eigenvalues as a series with corrections to the tree level result. And even that is not very beautiful. It's messy, but you can write it down. So for example, here, as I showed you earlier, that if you look at the tree level results, eigenvalue 1 and 2 are same. Eigenvalue 3 and 4 are same. And it's not surprising because at any graph here, you can see that they're at the tree level, which is small n5 behavior, the eigenvalues are the same, and they split later, right? Similarly here, you can see that two eigenvalues are the same and they split. There are two eigenvalues which are same and they split. So it's not surprising. So if you look at this series expansion, it tells you that eigenvalue 1 and 2 equals the tree level result plus these corrections. And these corrections, the expansion parameter is omega, where omega is given as this, right? And you can see that it's proportional to S. And if I remind you, S was proportional to lambda, as you can see here. So the expansion parameter has lambda in it, which means that the expansion parameter has one loop corrections. Okay, so these series expansions can be written down. They can be written down. They're not very pretty, but you can compare them with numerical results and they do match. Okay, now one thing that I haven't talked about yet are the vectors. What about vector fields? Are they above the BF bound? Now, the equations that you get for vectors are these equations, and it's not easy to convert them to a math matrix. Why? Because you have these terms. And how do you uncouple these terms to make these vectors into a math matrix? Suppose that these terms do not exist. Then you will have Laplacian of something equals some coefficient times the vectors, and that will be fine. But these terms make it difficult to make them into a math matrix. Now, there is one approach that we are working on right now, and that approach may tell us if the BF bound is violated or not. Okay, I'm going to talk about some future directions now. So one thing is is exactly what I said, that are vector modes stable for the background that we have studied, which is ADS 3 cross S3, and the previous background that I mentioned that was studied into the 2022, because in that paper, vector modes were not studied as well. So are vector modes stable perturbatively? We don't know. That's one future direction that I want to work on. Another thing is that in this whole talk, I haven't talked about torus moduli. I have talked about the perturbations that I introduced, but what about torus moduli? So we haven't studied them, but there is one thing that I can mention, and that is that torus moduli, the potential for torus moduli is generated because of the fact that this one loop correction is dependent on the torus moduli. So one loop correction is given as this, where lambda is coming from the partition function's integral, and you can expand it in terms of the torus moduli, right? I think I'm going to skip this slide because I'm running out of time. But one thing that you can do is that you can find out these derivatives and see if they violate the BF bound. Now, this is something that we are working on right now, but I don't have enough time to talk about this. Okay. Now, another question that I want to talk that's in our future plans is that what about ADS 3 cross S3 cross K3? Now, this was one of the motivations to study ADS 3 cross S3 cross T4. But one thing about K3 is that we don't know the metric on K3 in closed form, but there is hope at certain points. For example, T4 over Z2, that's a K3 point. It's called the Kummer point, if I'm not wrong. So that's one point that one can study. There are numerical metrics available on K3, but I don't know if they are useful enough for us to solve this problem. But there are certain points, for example, K3, T4 over Z2, for example. Now, what about non-perturbative stability? I didn't talk about non-perturbative stability in this whole talk. So what about non-perturbative stability of the background that we studied, which is this one, and the previous background that was studied in 2022? Now, one thing about these backgrounds is that they have multiple fluxes. And if you have multiple fluxes, there is this paper by Brown and Dahlin and Bosso and Polchinski, which argued that if you have multiple fluxes, then you can't have bubbles with small thickness, which is called the thin wall approximation. It was used by Coleman in his paper in 1977. So you have something called giant leaps, which means that you get rid of all the flux in a single bubble. And it's also called the bubble of nothing. This terminology was introduced by Witten in 1982. So if you have bubble of nothing and giant leaps, then you can't use the thin wall approximation that is normally used in these kind of processes. So that's why it makes things hard. And one more thing is that we have to worry about these kind of bubbles in torus moduli space. So these bubbles are just tunneling in moduli spaces. So what about tunneling in torus moduli space? That makes it hard, right, to study. So what we can do is that we can study a background that has no torus moduli. So what kind of background would that be? So one kind of background is ADS4 cross S3 cross S3. And you can see that there are no torus moduli here. This is just a 10-dimensional background with two fluxes, one flux being on one sphere. There is no flux on ADS4. And this is work in progress with Basile and Robbins. And the paper is almost complete. So you can see that there is no torus moduli here, that there are no torus moduli here, and we have found perturbative instability for some modes, in this particular background. But for non-perturbative decays, we have found that there are vacuua with small decay rate when these two fluxes are equal, right? So it means that when it comes to non-perturbative stability, the decay rate is small, and that means that the background is metastable. It's not stable, it's metastable. It means that it can live for a long time. But we don't know if the presence of torus or circle moduli will change this conclusion. So that's what we need to see by studying, for example, ADS3 cross S3 cross T4. So we don't know if it will change the conclusion. Okay, so that's it. Thank you for your attention.
Okay, so thank you very much, Hassaan, for this informative talk. And now I'm opening the floor for any questions that our participants have. So any questions from anyone?
Hi,
Yeah,
Hassaan. Yeah. So I have a question, not probably directly related to the talk you gave, but it's kind of like generic question. Say, for example, in type 2B, we talk about this ADS 5 times S5 background. That we can have because like we have this D3 branch and then we say that they are BPS objects, and that's why if you take some n of them and then take n tends to infinity limit, you get this ADS 5 times S5 kind of background.
Yes.
There we are like comfortable because this D3 brains are there as a BPS object in the spectrum of type 2B. But here I think you are taking some ADS3 kind of thing in the non-supersymmetric case. So how do you get this background? Can you comment on it a bit?
Right. So I don't know the exact brain configuration, by the way. that gives ADS 3 cross S3 cross T4 in the non-supersymmetric case. But the thing is, one thing that I can tell you, and you can look more into it, because I'm not an expert when it comes to branes and in the non-supersymmetric strings. But one thing that is very interesting about branes and non-supersymmetric strings is that the space-time literally ends if you try to go away from the brane in non-supersymmetric settings. So for example, there is this paper by Basile and someone else, I don't remember the other author. He has a paper on brane in non-supersymmetric settings. So when it comes to brane in non-supersymmetric strings, the picture is very different as compared to supersymmetric settings. But I'm not sure about the exact brane configuration that gives ADS 3 cross S3 cross T4, in non-supersymmetric settings.
Okay. Yeah, thank you. When Basile, you were talking about Ivano Basile.
Yes, Ivano Basile,
Okay.
yes.
I'll look into papers. Thank you.
No problem.
Okay, so any more questions? Okay, so if not, let's thank Hassaan for this very interesting, informative talk. And I also personally thank Hassaan for taking this initiative and giving the inaugural talk of our Stringy seminar series. So thank you very much, Hassaan.
My pleasure.
For other other participants, we will be having this Stringy seminars every fortnight. So we have a plan of like after every 15 days, we'll have a speaker who will give a topic related to he'll give a talk, or he or she will give a talk on string theory topic which are related to the current modern topics which are in trend. So thank you everyone for attending the first talk of this Stringy seminar series, and we soon will have other talks as well in coming future. So yeah, thank you everyone, and thank you Hassaan for this.
My pleasure. Yeah. Thank you for inviting me.